Here we're told that we have air entering the diffuser of a jet engine, so the diffuser is right at the inlet here. And the jet engine's operating at steady state at a given pressure, temperature, and velocity, all at the inlet here. All that information is given. And the air flows adiabatically through the diffuser and achieves a temperature of 250 K at the diffuser exit. So the diffuser is just the inlet part here. It's right before we go into the compressor. So the diffuser is just from 1 to 2 here. And we're given the temperature at 2. Using the ideal gas model for air, determine the velocity of the air at the diffuser exit. So we want to find V2 here. Okay, we're not concerned about the rest of the jet engine, just the inlet. So I'm going to draw a control volume around the diffuser section. And since I'm trying to find a velocity, that makes me think about wanting to apply conservation of mass and possibly the first law, since they both involve velocity. So let's try conservation of mass first to that particular control volume. So here's conservation of mass. And we're told that we're dealing with the steady flow here, steady state. So this term is 0. And so what we're left with is m dot in is equal to m dot out, which just means that m dot 1 and m dot 2 are the same. Let's just call it m dot for convenience. So we just have the same mass flow rate going in and going out. That makes sense. There's no mass, going through the sides or anything like that. Now to calculate that mass flow rate, if I wanted to find it, for example, mass flow rate would be the volumetric flow rate, like the velocity times the area, maybe at the inlet, divided by the specific volume there. Now I could find the specific volume because I have the pressure and temperature, and I could use the ideal gas law to find that, right? So I could do this to find the specific volume at the inlet. And I'm given the velocity at the inlet, so I know V1, but I'm not given the area, right? There's no area information given. So I can't calculate this mass flow rate. Without the area, I can't do any numerical calculation. All I know from conservation of mass is just the mass flow rate in equals the mass flow rate out. Okay, so that's as far as I can take that. Doesn't give me the velocity at state 2 here, which is what I'm looking for. So let me go to the first law. I'll apply the first law to that same control volume. So let's write it out. And it just takes a moment to write the whole thing out. There's a lot of terms. Okay, so here we are with the first law. Again, the first term 0 because it's steady state. Second term 0 because it's adiabatic. It's an adiabatic process. We're told that the air is flowing adiabatically through the diffuser, so there's no heat transfer from the diffuser to the surroundings here. So that's term 0. The power term is going to be 0 because a diffuser is a passive device. There's no work being done in the diffuser here. Okay, so that's a passive device. The potential energy terms, I'm going to set those equal to 0 as well. And the reason being is, first of all, we're dealing with air, which has a very low density. It's not, there's not a lot of mass per unit volume. And we're not dealing with large elevation differences. So these potential energy terms are very likely to be small compared to the specific enthalpy and the specific kinetic energy. So we're just going to neglect the potential energy as a reasonable engineering assumption because these other terms are just much bigger. So then, if we simplify the equation, we'll get the following. So here's the first law being simplified. And remember, the mass flow rate at the inlet and the outlet are the same. So since they're the same, we can just divide through by those, right? And then we can rearrange the equation here to solve for the velocity at the outlet. Okay, so I just did a little rearranging, and so now we can solve for V2. Since we're given V1, we still have to find H1 and H2. But at least if we can find those, then we should be in good shape to find the velocity at the outlet. So let's think about how we're going to find the specific enthalpies. Now remember, we're dealing with an ideal gas, treating the air as an ideal gas. So for an ideal gas, the specific enthalpy is a function only of the temperature. So I can use the ideal gas property tables to find the specific enthalpy at the two different temperatures. So if we use the ideal gas property table for a temperature of 216 Kelvin, it comes out to be 216 kilojoules per kilogram. The same thing for the specific enthalpy at T2, which we're given, was 250 Kelvin. That also comes out to be, so let's see, that comes out to be 250.0 kilojoules per Kelvin. It's just a coincidence that the specific enthalpy and the temperatures are the same in terms of the numerical value. That's not true in general, but at these lower temperatures, that's true. At higher temperatures, it's not true. Okay, so anyway, now we have all the information we need, right? We have the specific enthalpies. We know the velocity at the inlet that was given right up here is 265 meters per second. So we can solve for V2. And when you do that, V2 comes out to be 47.2 meters per second. It's a much smaller velocity, which is expected. Diffusers, that you can see the areas opening up, and that'll tend to slow from conservation of mass, that'll slow the velocity down. When you're dealing with incompressible or subsonic flows. So anyway, that's something you'd learn in fluid mechanics. One thing I should note, when you do this calculation here, you have to be a little bit careful. Remember, the velocities are in meters per second, and the specific enthalpies are in kilojoules per kilogram. There's a unit conversion that shows up pretty often here that looks like this. Let me just kind of show you from the very start. So you can take a kilojoules per kilogram. That'll be like a kilonewton times a meter per kilogram. And a kilonewton would be like 1,000 newton meters per kilogram. Right? And then that would be like 1,000 kilogram meter per second squared times meters per kilogram, which comes out to be 1,000 meter squared per second squared. So you can see 1 kilojoule per kilogram is equal to 1,000 square meters per square seconds. Okay, so you have to make sure you use that unit conversion when you're doing your calculation here to get the correct answer. This is a common mistake that I see with these kinds of problems, is where people forget to do this unit conversion. So don't forget that. All right, that's everything we need for this problem, so we'll end it there.